So here, let's look how it depends on the surface area, how we can conduct the experiment to find out it depends on the surface area. So we can repeat the above experiment with several lattice cube with different size but similar nature of surface. So we will always keep the same surface but different lattice cube. Using that, from the observation, we can prove that the emission depends on the nature of surface. Sorry, depends on the surface area. Okay, depends on the surface area. Next, temperature of the surface. So here, the Leslie's cube is filled with water at different temperature, and the radiation is observed. From observation, it is clear that the rate of emission depends on temperature. Okay, hope it's clear. And we also have another simple experiment to prove that black surfaces radiate more and polished surfaces radiate less. So that is Crookes radiometer. So the next experiment is Crookes radiometer. So here we have a small wind vanes, like wind vane like structures. So veins, we have 4 veins inside. Okay, so in these 4 veins, one of the side is black, one of the side is colored in black. So this side is colored in black, the other side is polished. So here this will be black, the other side is polished, and here we are able to see the polished side. Here also we see the polished side. I don't know, it's like a bulb. So these are veins. These are veins with black and polished surface. Veins with black and polished surface and polished surface on either sides. And here we have a very low air pressure. Okay. Now I'll explain what happens. After that, let's write down. When we place this, Crookes radiometer under light, if we place it in dark, if we place this one in dark, these veins do not move. They stay as they are. Okay. But when you place it under light, it starts to rotate. It starts to rotate. So there is something going on. Now, let's see why it rotates. As we discussed, this Crookes meter has two surfaces, right? One is black color surface. So this side is black surface. And on the other side, we have a polished surface. We have a polished surface. When light is incident on this surface, and as well as it is incident on this surface too, right? Look, at the same time, it is incident on a black surface and also on a polished surface. Okay, so both of them have equal chance to rotate in a certain direction. But this black color will absorb more heat. So this is going to absorb more heat than this polished surface due to the radiation. It is going to absorb more energy due to radiation than the polished surface. So if we compare the temperature of this black surface and the temperature of this polished surface, the temperature of black surface is going to be greater than the temperature of polished surface. Then when these air molecules, hit or collide with these two surfaces, when it collides with a black surface, it will gain a lot of momentum. It will gain a lot of energy when compared to colliding with a polished surface. Right? Is that clear? Therefore, now think the force on this side is greater than the force on the other side. I mean, when this molecule hits the black color surface, it will rebound with a greater velocity. Therefore, it will give a greater push. And on the opposite side, also molecule will collide and it will provide a force, but which is very small. So the resultant will be in this direction. So it will rotate. Now these are the veins and this side is black. Now, as I mentioned, the force in this side is greater. So it will start to rotate like this. Always the polished surface is in lead. Polish in lead. Is the idea clear? So because the polished surface is always taking lead, this has to be the reason. Okay, now we come in reverse. Did you all get it? Saja, how about you? Did you understand the idea? So draw this diagram. So write these points and see if you understood. This apparatus can be used to demonstrate thermal radiation. When exposed to light, black surface absorbs more heat than the polished surface. Therefore, black surface is always hotter. Molecules with the black surface colliding, okay, colliding with the black surface rebounds with a greater velocity than from polished surface. Hence, the vanes spin always with polished surface in lead. Okay, done. Raja. Okay, next let's look at a concept called the black body. Black body. Don't write, I will explain. After that, I'll give the note. So black body means it is an imaginary one, a idealized one. The idea of black body is uh, it can absorb, it can absorb all the wavelength falling on it. Whatever wavelength falls on it, it will absorb that. Now, um, just think about a black color body, black color object. So this is a black color object, okay? Why does this, when placed in sunlight or close to a fire, why does this heat a lot? The reason is it is absorbing the maximum amount of wavelength. It is absorbing the maximum amount of wavelength. But is it absorbing all the wavelength? No, it is still reflecting some of them. It is still reflecting some of them. How can I tell it is reflecting? If it if it is not if it does not reflect, then we cannot see this object, because think, light is also an electromagnetic wave. If it absorbed all the light falling on it, will you be able to see that object? No, right? Because we observe an object due to reflection. Is that idea clear? So, in nature, we don't have a black body, a real black body. Okay? It is an idealized one. So, the idealized black body, it can absorb all the wavelength. So, we cannot see that body at all. It will look like a black hole. At the same time, it can also emit. Now, if it can absorb all the wavelength, then it can emit all the wavelength, right? So this black body can emit all the wavelength. Draw these two diagrams. So this emits all wavelength, sorry, absorbs all wavelength. Absorb all wavelength. Emit all wavelength. Write these 3 points. Black hole is a body which absorbs all the radiation of every wavelength incident on it. So the concept of black body is an idealized one. And the third point, a black body can be made practically with a spherical cavity and a tiny hole. I will explain the third point. Done. Sarah, done. So let's look at the third point. The third point is mentioned that we can make a black hole practically with a spherical cavity and a tiny hole. It's like this. Now let's take a small cavity, a small spherical object. Okay. Now it's a spherical object. And in this spherical object, we have a small cavity, a small hole through which light can enter. So this light will enter through this cavity. Now we have a radiation that is entering through this cavity. And here, it might reflect back, right? Now if it falls at 90°, then it will reflect and get out through this cavity again. We have to avoid that. To avoid that, we are using a reflector. So a surface like this, something like this. Now the light is reflected into the cavity. Is reflected into the cavity. And during every bounce or during every reflection, certain amount of energy will be absorbed, right? Certain amount of energy is absorbed. Okay. So it will keep on reflecting off each and every surface until the energy is totally absorbed by this sphere. So whatever wavelength, now does this depend on the wavelength? No, right? Whatever wavelength you send through this cavity, that specific wavelength will be completely absorbed. So this can be thought as a practical blackbody, right? Is the concept clear? Did you get the idea what's happening here? Why we can consider it as a blackbody? Raja and Shahama, do you get, or shall I explain once? So sometime you might understand when writing this. Look, any radiation entering the cavity undergo several reflection, and during each reflection, some portion of the energy is absorbed. And finally, the radiation is completely absorbed. Since any radiation entering the hole is completely absorbed, the hole can be considered as a black body. So the type of radiation doesn't matter at all. It will absorb any. A surface which absorbs thermal radiation well can emit them out well. Write these 3 points also. I will explain them. A simple question. Now let's say we have some water in two containers. Okay, we have water in two containers. One of the container, it's black in color. This is black in color and this is polished. And you have a thermometer within both of them. Now, A, B. When we radiate using certain source, which one will heat up first, heat up quick, A or B? Which one will cool first? A is the answer. Now the question is which one will cool first? A or B? Saja, what do you say? The answer is A. The answer is A. The idea is which is the best radiator? I mean, which one will absorb the radiation more? Black color will absorb the radiation more. Okay, it is a good absorber as well as it is also the best emitter. Okay, if a body is good at absorbing the radiation, then it is also good at emitting the radiation. So black color will heat quick as well as the black color will cool quick. Is the idea clear? So that is what we have mentioned in the next 3 points. A surface which absorbs thermal radiation well can emit them out well. Once you have noted, let me know all the points. Done. Saja. How about the third point? The rate of heat loss of a black body depends on the temperature and the surface area uh, only, not the nature of surface. What is the reason? Not depending on the nature of surface. Now it is already a black body, right? That means it will always be black in color. I mean, it will be black. At the same time, it will always emit all the radiation. So, if it is a black body, then again, it is not going to depend on the nature of surface. Okay, the rate of heat loss won't depend on the nature of surface. Hope that idea is clear. And then you have when when we heat a metal, have you seen that the metal becomes red in color? So uh, when we heat a black body, when heated to high temperature, it will emit all type of radiation which it was able to withstand. So now this is not a black body. This metal is obviously not a black body. But when you heat and it comes to a specific temperature, it releases radiation. Okay, it releases light. So we can see red color. Similarly, if we have a black body, and we heat this to specific temperature, then this will release uh, radiation. It will give out visible light. And for another temperature, let's say another temperature TB, it will give another light, another visible color. So here, when it comes to a metal, the colors are limited. It can only release few wavelengths, but this black body, it can release all the wavelength. Okay, hope the idea is clear. So next we have Stefan's law. Stefan's law. When we take a black body, this is going to emit radiations depending on the temperature. When the temperature is T, it will emit radiation E. I mean energy E. So what Stefan says is the total power radiated from unit area. The total power radiated from unit area. So that is E here. E is not energy, it is power per area. Okay, power per unit area. is proportional of a black body is proportional to the fourth power to the fourth power of the temperature of the body, temperature T of the body. So according to him, E is proportional to T to the power 4. And this should be absolute temperature. Absolute. So we can convert this into an equation by introducing a constant, and that is sigma. We call this constant as the Stefan's constant. Sigma is Stefan's constant. And its value is 5.7